Good day. This is MEG224 Engineering Mechanics 2 Dynamics. We're looking at lecture 5B, Kinetics of a Particle, the Principle of Impulse and Momentum, Part B. Therefore, this topic can be found in Chapter 15, Engineering Mechanics, Dynamics by R.C. Hibbeler. Lecture objectives. Number one, we're going to introduce the concept of angular impulse and momentum, and then use it to study the conservation of angular momentum for particles and system of particles. Angular momentum. The angular momentum of a particle about O is defined as the moment of the particle's linear momentum. The moment of the particle's linear momentum. What it's saying is that you have to find the linear momentum first. You have to flip it about O, and then now find the moment of that linear momentum. So since the concept is analogous to finding the moment of a force about a point, the angular momentum is sometimes referred to as the moment of momentum. Moment of momentum. So we have two types of formulation for moment of momentum or angular momentum. The first formulation is scalar formulation, and the second formulation is vectoral formulation. The scalar formulation is what we're going to look at first. If a particle moves along a curve lying in XY plane, as shown in this figure, the angular momentum at any point or at any instance can be determined about point O. Actually, that's the z-axis by using scalar formulation. That is, the particle is moving in XY plane, and then the angular momentum will be found about this point O, and then the angular momentum is pointing upward in the direction of the thumb, where you fold your fist in this direction. So the magnitude of angular momentum HO is HO about z-axis is d dot mv. That is d, that is the moment arm, or the perpendicular distance from O to the particle that is having the velocity mv, or that possesses velocity v with mass m. So common units for angular momentum about z is kilogram meter square per second. Kilogram meter square per second. D is measured in meters. V is meter per second. So that will give you meter square per second. And mass is in kg. So the direction of HO, that is angular momentum, is defined by the right-hand rule. As shown, the core of the fingers of the right hand indicates the sense of direction or rotation of mv, that is the momentum, about O, so that in this case, the thumb HO is directed perpendicularly to XY plane along the z-axis, thereby forming three triaxial axes, three perpendicular axes, X, Y, and Z. The particle is moving in the XY plane, and the momentum is directed upward. The angular momentum is directed upward. And the direction of movement of the particle is counterclockwise. We know that in mechanics, counterclockwise or anticlockwise is positive. So let's now look at vectoral formulation of angular momentum. If the particle moves along a space, as shown in the figure, the vector cross product can be used to determine the angular momentum about O. So the particle here now is not moving in the XY plane, but it's moving in the XYZ plane. That is, the plane is not flat. The particle is not moving in a flat plane, but it's moving in the three space. There is three axis space that is in the space. So in this case, angular momentum is equal to R cross mv. Cross is the cross product. Cross product. Here, R denotes a position vector drawn from point O to the particle. As shown in the figure, H naught is perpendicular to the shaded plane containing the R and mv. R is the distance from the particle to the origin, or from the origin to the particle, while mv is the momentum. In order to evaluate the cross product, R and mv should be expressed in Cartesian terms, and then so that the angular momentum can be determined by evaluating their determinant. We know that R will be Rx I plus Ry J plus Rz K. Yv will be Vxi plus Vy J plus Vz K. But now, what will M be in XYZ plane? So now let's look at how to calculate the determinants. So we now have I, J, and K, Rx, Ry, and Rz, Mvx, Mvy, and Mvz. So let's look at the relationship between a force and angular momentum. The moment about point O of all the forces acting on the particle in figure A can be related to the particle's angular momentum by applying the equation of motion. So this is the particle. This is the particle in space. A force is applied to it, or the sum of all the forces that are applied or that are acting on it is in this direction. So if the mass of the particle is constant, we may write that summation F is equal to m v dot, and v dot is time derivative of v, which is acceleration. The moment of the forces about O can be obtained by performing a cross product multiplication of each side of this equation, by the position vector R, which is measured from the XYZ inertial frame of reference. We have summation m naught, that is the total moment the total moment is R cross summation F, which is equal to R cross V dot, or R cross A. The derivative of R cross FV can then be written as H naught is equal to d dt of R cross MV. R cross MV. So, and when you open up this, you do what we call, you use what we call product rule. So, d dt of R is R dot, and you keep this part. Then you cannot differentiate M because M is constant. If not, you will have had to differentiate it first using product rule. So now you keep R constant, M V dot. So the first term on the left is R cross MV. Sorry, R dot cross MV, which is equal to V is velocity, which is the time derivative of displacement. R dot 2 is velocity. You see that you say V cross V or R dot cross RV, R dot, sorry. And you know, in cross product, when two vectors are facing the same direction, the angle between them is 0, and sine 0 is equal to 0. Since the cross product of the vector itself is 0, so hence the above equation becomes summation M naught is equal to H dot naught, or H naught dot. So which says that the resultant moment about point O of all the forces acting on the particle is equal to the time rate of change of the particle's angular momentum about O. This result is similar to this. Summation F is equal to L dot. And L in our first lecture is MV, that is linear momentum. Linear momentum, that is mass times velocity. So here, L is equal to MV, so that the resultant force acting on the particle is equal to the time rate of change of the particle's linear momentum. From the derivations, these two equations are actually another way of stating Newton's second law of motion. When we now, let's now look at system of particles. An equation of the form summation M naught is equal to H naught dot will be derived for system of particles shown here. You know, we have particles moving randomly in a system. The internal forces are collinear, they appear and collinear, and then they cancel out in the summation when you are looking at the forces. So the forces acting on the arbitrary ith particle of the system consists of a resultant external force, Fi, and a resultant internal force, small fi. Expressing the moment of these forces about point O and using the form which we have already established earlier, then we have Ri cross Fi plus Ri cross Fi is equal to this. So here, Hi dot O is the time rate of change in the angular momentum of the ith particle about O. Similar equations can be written for each of the other particles of the system. When these results are summed up vectorially, the result is, just put a summation sign, so that it shows that you are summing all the terms for each particle together. So since the resultant internal force is always 0, so Ri cross 0 will give you 0. So the second term is 0 since the internal forces occur in equal but opposite collinear pairs, and hence the moment of each pair about point O is 0. Dropping the index notation, the above equation can be written in a simplified form as that. So, which states that the sum of the moment about O of all the external forces acting on a system of particles is equal to the time rate of change of the total angular momentum of the system about point O. Although O has been chosen here as the origin of coordinates, it actually can represent any fixed point in the internal frame of reference. Principle of angular impulse and angular momentum. If summation MO, that is a moment about O, is H dot naught, is written in the form of this because this is H dot is time rate of change, d dt. So we now put the t, bring it here by a cross multiplication, and d is left here, and integrate, assuming that at time t is equal to t1, h naught is equal to h naught 1, and at time t is equal to t2, h naught is equal to h naught 2. So this one should be 1. We have that integral from t1 to t2 m naught dt is equal to h naught 2 minus h naught 1, or h naught 1, that is, we are taking this guy minus h naught 1 to the left hand side, and that minus becomes positive. So plus h plus integral t1 to t2 m naught dt equals h naught 2. This equation is referred to as principle of angular impulse and angular momentum. The initial and the final angular momenta, h naught 1 and h naught 2, are defined as the moment of the linear momentum of the particle. H naught is equal to R cross MV at the instants T1 and T2, respectively. The second term on the left-hand side, the integral m naught dt, is called the angular impulse. It is determined by integrating with respect to time the moment of all the forces acting on the particle over a period of time T1 to T2. Since the moment of a force about point O is m naught, which is equal to R cross F, the angular impulse may be expressed in vectorial form as angular impulse is equal to m naught dt, which is equal to integral Rf dt. Here, R is a position vector which extends from point O to any point on the line of action of F. In a similar manner, using this equation, the principle of angular impulse and angular momentum for a system of particles may be written as this. This is for a particle, and this is a system of particles, or a system containing particles. So you sum everything together. So here, The first and the third terms represents the angular momenta of all the particles. Summation H naught is equal to summation Ri cross MVI at the instance of time T1 to T2. The second term is the sum of the angular impulses given to all the particles from T1 to T2. Because that these impulses are created only by movements of the external forces acting on the system, where for the ith particle, M naught is Ri cross Fi. Vector formulation. Using impulse and momentum principles, it is therefore possible to write two equations which defines the particle's motion, namely mv plus integral f dt is equal to mv2, and h naught 1 plus integral m naught dt from T1 to T2 is equal to h naught 2. So scalar formulation. In general, the above equations can be expressed in xy components, yielding a total of 6 scalar equations. If the particle is confined to move in the xy plane, 3 scalar equations can be written to express the motion, namely mvx1 plus integral fx dt mvx2 in the x direction, mvy1 plus integral fy dt mvy2 in the y direction, and h naught 1 plus integral m naught dt is equal to h naught 2 in the z direction. Here, we know that the particle is moving in the xy plane, and then the angular momentum will be in the z plane. So this is the angular momentum equation, and these two are linear momentum equations. So the first two of these equations represents the principle of linear impulse and linear momentum in the xy directions. And then the third equation represents the principle of angular impulse and angular momentum about the z axis. So conservation of angular momentum. When the angular impulses acting on the particle are all zero during the time T1 to T2, then h naught 1 plus summation of m naught dt h naught 2 reduces to the following form, because this term is angular impulse. It cancels out. Then left-hand side now becomes right-hand side. So this equation is known as the conservation of angular momentum. It states that from T1 to T2, the particle's angular momentum remains constant. Obviously, if no external impulse is applied to the particle, both linear and angular momentum will be conserved. In some cases, however, the particle's angular momentum will be conserved and the linear momentum may not be. An example occurs when the particle is subjected to a central force. As shown in the figure, the impulsive central force is always directed towards the point O as the particle moves along the path. Hence, the angular impulse created by force F about the z-axis is always zero, and therefore the angular momentum of the particle is conserved about the axis. From equation 20, we can also write the conservation of angular momentum for a system of particles as. So it's still the same thing as what we have gotten. In this case, the summation must include the angular momenta of all the particles in the system. Thank you. End of part B. So please do not forget to like, subscribe, share, and press the notification bell for new videos. If you are one of my university undergraduate students, please do not forget to subscribe with your real name, and then you will have new updates. Thank you.